right, so this video is going to be on radical halogenation at an allylic carbon. And so what I want to do is, well, first of all, I got to remind you what an allylic carbon is, um, but we're going to use cyclohexene to do that. Okay, so let's just imagine we could halogenate something, and what would the product be with this particular cyclohexene molecule? We've got three different types of hydrogens: a red, a blue, and a pink one. And what we want to do to determine what the product is going to be in a radical bromination process, is look for the weakest hydrogen, the CH, because by definition, bromination is selective, and it's going to basically substitute the hydrogen that has the weakest carbon hydrogen bond, right? So if we look at those numbers, we got 402, 364, and 444. So that allylic position is the weakest at 364 kilojoules per mole. So it's quite significant too. And we do have two of them, so we can end up with two different products in theory, but this particular cyclohexene molecule will yield the same product, right? And only if we had some substituents on that cyclohexene ring would we be able to isolate two different types, okay? Now, we are taking a look at the allylic radical that's formed. And so the question is, why is this so low in energy? Well, in theory, in terms of energy, that's so low because it's stable, but it's a secondary CH, right? Well, not technically, because it's an allylic CH, right? That's different than the adjacent pink CH, which is significantly higher in energy. And I just kind of want to remind you that allylic carbocations and benzylic carbocations were pretty stable. And even though they might seemingly be primary carbocations, they aren't. And that was because of resonance. So you could draw a resonance structure for the allyl right here, basically giving us the shift in the carbocation as well as the pi bond. And the same thing for the benzylic compound. The carbocation moved and the double bond did as well. And so that's what we can do with this allylic radical. And so I'm going to redraw it down here just so we can have more space to draw, but we're shifting around the electrons only in the p orbital, remember. Okay, so this is the radical that we would end up with. Now, because the cyclohexene is symmetrical, it's really the same thing, and that shift doesn't do anything in terms of the halogenated compound or product. But if there were substituents on that cyclohexene, you would end up with something different, right? Otherwise, it's the same as those two. All right, so now what we want to take a look at is the general trend for radicals. And we've seen this before already in the previous videos, so let's just go ahead and draw what we know already. And that would be like a methyl radical, then we got our primary radical, our secondary radical, and then our tertiary radical, right? So what's the general trend for these guys? As we go from left to right, what is that? That's going to be an increase stability for these radicals, okay? And again, that was because these carbons that have the radical on it are electron deficient, and those R groups help stabilize it. Now, the allyl actually lies on or to the right of the tertiary radical. Okay, so, sorry, let me get this better. I'm going to go ahead and draw R groups just to let you know that it doesn't have to be the simplest allyl. It could be more complicated allyls like the cyclohexene, right? So those R's could be the same. They could be hydrogens. They could be different. It doesn't matter. But I just want to let you know, like, an allyl is basically a pi bond, like an alkene, and then on that the carbon that's bound to the sp2 carbon is going to have a radical on it. So we're going to draw a couple out and just give you some examples and help you identify really how this resonance kind of works as well. So remember that we have p orbitals right here for the pi bond, and then we have a p orbital that the radical resides in, right? And so we have 3 or more consecutive p orbitals, and that's really what we want in order to do a resonance. Okay, so the p orbital could be vacant, like in a carbocation, or it could be occupied, like in this case, right? And so, since we kind of have meet that criteria, we can do a resonance structure by shifting those pi electrons. Okay, and so that's what we end up with here. Just a radical at a new position. Same thing with this cyclohexene right here, right? I just want to show you. Boom. Remember the half arrow, the fish hook arrows for the movement of a single electron. And so we've got this guy right here. All right, now let's take a look-see at, I want to draw you a compound, and then I want you to decide what the possible products are going to be, okay? So we have this particular methylene compound. So let me go ahead and write a real question of what you might actually see on a quiz or an exam or something. Okay, so I want you to predict the products that are obtained when methylene cyclohexane, the compound below, is treated with NBS. I'll explain what that is in a little bit, and irradiated with UV light. Okay, now I should probably do this problem later, but I really wanted to do it now, so I'm gonna do that. NBS, I'll have to explain shortly what that is, but let's just remember from last semester that it's a source of BR2, right? And NBS in this case is still going to be a source of BR2. It's just a different mechanism because it is a radical mechanism. Okay. And so for now, we can think of it as a source of BR2 for a radical addition to an allylic hydrogen, right? And so because we have that hydrogen there, let's just imagine we form a bromine radical somehow, some way. It keeps coming at me like every single day. A bromine radical. Okay, we got two of them right here. Let's just say, for example, now what we want to do is, let's see, we've got our alkene there, and then what we want to do is kind of identify the weakest CH bond, right? And then we're going to swoop on that proton or that hydrogen atom. And we obviously, this is the allylic position, and this is what it's going to look like with our fishhook arrows, right? We will have that bromine radical attack the hydrogen atom, and then making the methylene cyclohexane radical. Okay, and now this species right here looks a lot like these above, right? And the above species had resonance structures. So that's really what you got to look out for when you're working with allylic compounds, allylic radicals, or even allylic carbocations, right? They can form resonance structures, and therefore you have the possibility of forming more than one halogenated compound. Okay, so this guy right here, and the one on the left has the methylene CH2 on the end, and then the one on the right, it shifted the pi bond, right? And so remember that the radical does attack a elemental bromine, a bromine molecule, and what that does is ultimately adds a bromine atom to that the position where the radical was, right? And so it's going to look like this, where you have the fishhook arrows kind of breaking this bad boy apart. And now we can draw the product. So everything stays the same, except now that radical now has a bromine instead. Okay. Now let's do the same thing for the allylic radical on the right. And it's the same process, except it's just at a different position. And so really easy to jump to the final step and throw a bromine on the allylic positions. And so notice that each of those carbons was the terminal position on that 3 consecutive p orbitals. And so that's kind of how I envision it and jump straight to the final product. I put 4 stars on here and a smiley face because this is that good stuff, and you should definitely make sure you know how to do these, okay? But I'm sorry, oh Cam. I kind of lied. Like, kind of maybe lied a little bit. I apologize. Because MBS is a source of BR2, right? It's not really BR2, and a lot kind of happens in this radical reaction with MBS. So I'm going to basically explain to you one of the issues with having the BR2 only, and that would be the competing addition reaction. Remember, so an alkene with elemental bromine actually gets you your dihalide, your dibromide, right? And so if that's a competing reaction, like that's not good. You're going to end up with a mixture of materials. Technically that's 3 different products that you can get now, and so that's not good. It's a waste of material and money and time. And so NBS with light or a peroxide or something, some radical initiator, that will get you your allylic bromide as the major product, and none of this guy right here. Okay, maybe the tiniest bit of that could be possible, but it's just not statistically likely. And I'll tell you why. First, let me explain to you why MBS is your source of bromine in this particular reaction. So in the presence of light, it will break apart. And so check it out. Boom, what's up? Raw. H new. Break up. Homolytic cleavage. And you get your N dot and your BR dot. Okay. Now, we don't care about N dot. Bye, Felicia. Like, we don't need that. So BR dot is what we want. Okay. So we'll bring that down here and we'll use it. That's the initiation step, right? So now we swoop on our weakest CH bond and we get our allylic radical, right? So now that we've got our allylic radical and HBr, don't forget about that. It's important later. We have BR2 present, and we do attack, and we get our substitution at the allylic position. And okay, so here's the thing, right? So where did the BR2 come from is the question, right? And that's again where the NBS comes into play. So we have NBS right here, and then HBr, which we got from our this step right here, the formation of the HBr after we remove that proton or that hydrogen atom, sorry. And the NBS in the presence of HBr actually gives you a little swoop-de-swoop, and you get the NH bond and BR2 forming. And so that BR2 is then used in the final step to make that allylic bromide, right? So since this process requires the HBr, which comes from the radical reaction, it's very low concentration. The BR2 is, And so the BR2 being in very low concentration means that we have a very small probability of having the addition reaction occur where we have the dihalide forming. Okay, so, and also remember here, this is the mechanism. We have kind of like a double attack going on to form that bromonium ion. And then not only do we have to have that occur with the BR2, but we also have to have a Br minus come back and attack that bromonium ion. But that Br minus, he's floating around in solution. He's on his way, checking some other things out. And so the likelihood of, if you have a very low concentration of BR2, you have a very low concentration of bromonium ion and bromide. And so all of these things being able to come together is just not statistically likely when you have a halogenation reaction occurring in conditions that promote a radical mechanism, right? And so that's basically what I'm getting at is the allylic halogenation must be done with NBS to avoid competing addition reaction, right? That guy right there. And this is going to allow us to more or less selectively form the allylic bromide. Okay, and so what we want to do here is get some practice, y'all. So I want you to be able to identify the allylic position. Not only that, but any possible products that can be formed if a resonance structure were to be formed. Okay, so I don't like the fact that I used formed and formed. It's like I'm just doing some lame rhyme right now. So here, let's see, 1, 2, 3. Let's do 4-ish structures. Okay, so let me draw them out. What I want you to do is pause the video, and then try them on your own, and then check back and see if you get the same thing that I get. Okay, so first draw out the bromine substitution at the allylic position, and then after that try and see if there are any resonance structures and new products that can form from that. Okay, so let's draw red dots on the carbons of interest. Right, so these are all possible options for, these are allylic carbons, right? But these ones with the red X through them, those are not possible options because they don't have an allylic hydrogen, right? So let's try blue dots. Now these blue dots right here kind of, in this case, they have allylic hydrogens and therefore are options to kind of use to proceed for using MBS and light and to give us an allylic bromide. Okay, so allylic bromide would look like this, and this is the product based on keeping the pi bonds in the current positions. Okay, so we'll take a look at the resonance structures after. But red dots again are the 3 carbons of interest, right, involved in that allylic kind of compound or functional group. And then the blue, right, those are also the 3 adjacent carbons that might be of interest, but the blue one in this case is not an option, and because it doesn't have an allylic hydrogen. So we only end up with the product on the right. Okay, now let's draw the 3 of interest. If we were to draw the blue ones now, these 3 are of interest as well, but if you look closely, this molecule is symmetrical. So each of those allylic positions is equivalent, and we can really only form one product. And so that's what we're going to draw. We have our, basically, if you haven't noticed, basically all I do is draw out the same exact compound, but then since the hydrogen wasn't drawn explicitly anyway, you could just throw a bromine at the allylic position if there was a hydrogen there. So pretty sweet. Easy way to jump to the product. This guy right here, you've got only one possible position that's with the pi bond in its current position. And so there we go. We draw out the same compound and then just draw the bromine at the allylic position. Perfect. Okay. So what about when a resonance occurs, right? That's the question. So we have to remember that that pi bond can basically move to where that bromine is in the first compound that we drew. And so if we do that, we can kind of shift that pi bond. And when it comes to drawing the mechanism, obviously use the the hook, fish hook arrow. But when I'm thinking of it in my head, I just think of it as a normal resonance structure, like a carbocation rearrangement or something. And so that's what I did in my head. I moved the pi bond through the bromine where the pi bond used to be and is no longer. And then same for this one. If you take a look at these 2 compounds, little rotation right here will give you the same compound on the left. Okay, so this actually doesn't change the outcome. There's only one product in this case. And for this guy, if we do a little resonance structure, kind of shift that pi bond over, we get this guy. And that's all she wrote. Now shift this bad boy over, we get this tri-substituted alkene with a bromine at the terminal position. And that's all she wrote. That's basically halogenation with bromine, specifically at the allylic position. Remember, it's all about that MBS. So anytime you see MBS with light specifically, you're thinking allylic bromination. Okay? Have fun with it. Let me know if you have any questions. Bye. Oh, you know what? I heard a joke today. Like, no joke. Heard a joke. My daughter told Alexa, "Tell me a joke." She's 2.5, by the way, so she knows what's up. She said, Daddy needs some more material for work." So, uh, what was it? I'm making this video longer than it needs to be. Um, okay, so why was the chiropractor late for dinner? Because he had back-to-back appointments. Oh, that's so bad. I'm sorry. It probably doesn't even go like that, but it was something like that. Chiropractors back to back. You get it, right? Okay. Have fun. Bye.